So we are going to discuss accelerated rotation today, and as we go through these notes, we are going to be using free body diagrams to identify whether a system has angular acceleration. We are going to calculate angular acceleration from net torque and moment of inertia, and we are going to apply equations for moment of inertia for basic shapes to angular acceleration. So we're going to do really just one example calculation, but you're going to see it does have quite a few steps in the derivation, so I would encourage you to copy it down because I know how much you guys love derivations. So it would be a good example to have so that you can look back at it later. Again, these are the first notes that we are working on in playlist 3. However, today is the due date for all of your task options in your checkpoint for playlist 2. So when we're done with these notes, if you haven't finished those things, you can work on that. And you do need to make sure that you get your torque lab turned in. But you can also start working on playlist 3 after we've covered these notes. As a reminder, tomorrow is SAT testing. We will have a very shortened period, and there is nothing planned specifically for class tomorrow. So whatever time you do have, you can use to work while you're in here. All right. So angular acceleration. An object will experience angular acceleration when there is a net torque not equal to 0. Okay, so if you have a net torque, a force that's going to cause rotation, and that net torque is not 0, then of course you're going to get rotation, and that's going to cause acceleration of that rotating body. The equation that we're going to use to calculate this acceleration, we do have more than one equation. You guys have seen this variable alpha before. It showed up in our kinematic equations for rotation, but you can also get a rotational equivalent to basically F equals ma, except for if we're going to have torque equals I times alpha. Okay, torque is your rotational equivalent to the force. Alpha is your rotational equivalent to acceleration A, and moment of inertia I is the rotational equivalent to mass, okay, or the translational values for those. So again, we can write that as A equals net torque divided by I. You could write it as net torque equals I alpha, okay, but it's the angular equivalent to this equation, our second law equation. Net torque and angular acceleration have a direct relationship. Again, you can see that in the equation. Moment of inertia and angular acceleration have an inverse relationship, and again, you can see that in the equation. By the way, this equation will only be useful to you if you have a constant angular acceleration. Of course, if you have an angular acceleration that is varying over time, then you won't be able to use that equation. That's true with the kinematic equations as well. Okay, so it's for constant angular acceleration, which is pretty much the only thing we deal with in here. So again, new equation, alpha equals net torque divided by I. That's angular acceleration equals net torque divided by moment of inertia. So, common scenario where you could see something like this, and there are, of course, more than just this one, but pulleys. We've looked at pulleys already once before. You had those in your RA on moment of inertia, but a pulley rotates about its axis due to tension of a rope or string that pulls at some radius away from its axle, causing a torque. So the pulley will actually rotate because of the torque applied from that rope that is going over the pulley. And so you'll get a rope pulling at some distance from that center axle, causing torque, causing a rotation, and thus an angular acceleration of the pulley itself. Note that the tension is caused by an object pulling on the rope or string. If you're looking at the acceleration of the objects that are falling or rising, it's technically going to be a linear acceleration. It's just the wheel itself that's going to give you that angular acceleration value. To relate an object's linear acceleration to the pulley's angular acceleration, we do have equations to relate the two. We've talked about it already before, but you can just take that acceleration and set it equal to alpha times radius, or you can say alpha equals acceleration divided by radius. And we talked about how we can always get from our angular values to our translational values, or vice versa. With an equation like this, it was the same for all of those different variables, same pattern. We looked at that earlier in the notes. Okay, so if you do know the acceleration of the falling mass, you could convert that into angular acceleration with that equation. And again, I didn't ask you to do that in the RA that we did because we hadn't learned this yet, but we could have gone back and done that because all the values you collected were technically linear accelerations because you were getting data from the falling box, or falling mass rather, whenever you did that lab. All right, so steps to solve these problems. These steps should look familiar. You have seen them before. We talked about this already with some of our other rotation problems, but step 1 is still the same. Choose your axis of rotation. Okay, an ideal location for an axis of rotation is one where there are the most unknown force values, because if you have forces applied at the axis of rotation, they do not cause a torque. And so it's helpful to analyze it with your axis of rotation being at that point where you have the most things that you don't know, because then it takes those out of your equation. Step 2, draw a free body diagram. Again, step 2 can help you identify how you should choose your axis of rotation in step 1 if you're not sure. Draw that free body diagram first if you like. Again, as a reminder, rotating objects are rigid body systems, and so we do need to make sure that we draw those forces from their point of contact. The position at which they're applied matters. We're aware of that because we've been doing that torque equation, and part of that equation includes the radius or the distance that force is applied away from that axis of rotation. So of course that position is going to matter. So you need to make sure to draw them as rigid body systems. Step 3 is going to be to write the net torque equation for your counterclockwise torques, and then do the same thing for your clockwise torques. And so you'll have alpha equals net torque counterclockwise divided by I, that's your moment of inertia, and then same thing, alpha equals torque net clockwise divided by I, and those will be the net torque equations for both clockwise and counterclockwise, and then of course you can use those to solve the problem. Okay, so these steps, again, we have seen things like this already when we did some similar problems earlier on. It's just that the equation we're using here is different than it was previously because we were doing a net torque equation instead and net force equation. But similar process. So let's try it and apply this to an example. Again, this will be a good thing for you to copy down onto your paper so that you have it to refer back to as you're trying to work through similar problems in playlist 3. This question says a beam of 7 kilograms was initially held in place by a cable as shown. Determine the angular acceleration of the beam after the cable is cut. Note the falling beam acts as a rod rotating about its end point, so its moment of inertia, I, equals 1/3 ml squared. Remember, I told you that you don't have to memorize those moment of inertia equations for those shapes because they'll be given to you in a question. So here is the equation for the moment of inertia for a rod rotating about its end point. Okay, so we have 1/3 ml squared. All right, so again, first step is to determine our axis of rotation. Okay, my axis of rotation, obviously it's going to rotate about the hinge. So this one's a little bit more obvious than some of them are. So I'm going to put my axis of rotation here. When I go to draw my forces, you're also going to see that I have more forces there as well. If you weren't sure, you could of course start here with a free body diagram. Okay, so we're going to draw a free body diagram showing the forces acting at their point of contact. So we'll go ahead and start with the normal force from the wall because this is up against a wall, and so we have a normal force, that perpendicular force from the surface of the wall being applied to this rod. Okay, we also have the force of the wall or the hinge on the wall or the friction, whatever you want to call this, but you have this force, this upward force that's keeping it supported at that position as well from the hinge or from the wall. I labeled it as F wall. Okay, what other forces should we include?
Gravity.
Yeah, we should include the weight of the object, the force of gravity. And we're going to assume an even mass distribution. I have that note down here at the bottom. It does say the beam has mass. Sometimes the question will say it's a massless beam. And then you don't have to include that, but it'll have something on the beam then. But in this case, we need gravity, and if we have an even mass distribution, I need to draw my force of gravity at my center of mass, which is going to be in the center of my rod. Okay, at least I tried to draw it in the center of my rod. It might not be perfect. That's okay. Try to draw it as close to the center of your rod as you can. Okay, so those are the forces that we need to consider. So the next step is to write our net torque equation. We're going to start with the counterclockwise direction. Now remember, because my axis of rotation is at the hinge, neither this F wall nor this Fn causes rotation. That means I only have one force that's causing my net torque, and that's Fg. Because everything else, there's only two other ones, are at the axis of rotation. Fg would cause rotation about this point in this direction. Okay, if you imagine it pivoting around this point, it would cause it to rotate in a clockwise direction, not a counterclockwise direction, which means my net torque in the counterclockwise direction is just 0. Okay, I don't have any torques in the counterclockwise direction, so my net torque there is 0, and thus my angular acceleration in the counterclockwise direction is also 0, because it's not going to accelerate that way. Okay. However, if I look at the clockwise direction, I do have a force causing a net torque, and that is the torque due to the force of gravity. And so I can put that in and say that my angular acceleration alpha equals that torque due to the force of gravity, that is my net torque in the clockwise direction, divided by I, which is my moment of inertia. If I substitute in, I can get this. Fg, again, that's my force of gravity, times r sine theta, again, that's my torque equation, Fr sine theta, divided by I. And we have some more substitution steps that we can do, because again, we are trying to determine that angular acceleration, which means we need to get this in terms of some variables that we do know. Okay, so let's go ahead and keep going. Okay, if we want to go ahead and solve for alpha now that we have our equation written, we're going to start, again, here's that same equation up here rewritten, alpha equals FGR sine theta. I'm going to start with this, divided by I. I'm going to start with this I, this moment of inertia, because it tells me in the equation what to use for moment of inertia for this rod. And it says to use 1/3 ml squared, so let's go ahead and do that. Okay, so I substituted that in. I've also substituted in mg for Fg, because again, Fg is your weight, it is mass times your gravitational field strength, so that's in there too. So I have mgr sine theta divided by 1/3 ml squared. Okay, what would be my r? What is my lever arm length here? Okay, yeah, it's going to be half of that total length. The total length is 10, okay? And so it is 5, but I'm going to do it in terms of variables. Okay, so I have L over 2 in there for r. And now I have mg times L over 2 times sine theta. Yes, if you want to plug a 5 in, you can. Again, I'm going to do it in terms of variables, because sometimes you're asked to derive an equation without having any numbers. So again, for those derivations, keeping the variables in there is probably a helpful practice. Okay, radius is between the force and the axis of rotation. So since that Fg was at the center of mass and you guys got this, you know that that is going to be 5, or half of the total length. So we've got this now. Looking at this, I can cancel out these masses because I have one on top, one on bottom. Everything's multiplied. I can also cancel out this L and one of these, because I have L squared down here and I have L up here. Okay, and so I can get a simplified, or at least a more simplified looking expression. Since I divided by 1/3, I may as well put that 3 up here. Since this is g over 2, I may as well put the 2 down here. And so here it is looking a little bit more simplified. I have 3g times sine of 90, because that is my angle, the angle between Fg and the rod is 90 degrees, divided by 2L. And guys, what's sine of 90? 1. Okay, so I can get rid of that too. And so I end up with this. Alpha equals 3 times g over 2 times L. That seems like it might be a helpful derivation for a problem that looks similar to this, because that is a much easier equation to work with than what we started with. And it was a lot of steps to get there. Okay, so let's go ahead and solve, because we know g, we know L, we can plug in, we can solve for alpha. Again, g is our gravitational field strength on Earth, that's 10. The length of this rod, that's 10, it's in the picture. So I have 3 times 10 divided by 2 times 10, which of course is just 3 divided by 2, or 1.5. Okay, units. I need units on my angular acceleration. What are my units for angular acceleration? It's something. Yeah. Okay, radians per second squared. You can write it as radians per second. Okay, but don't forget those units. Okay, and then we also need a direction. What is the direction of this acceleration? Again, this is all due to that force of gravity Fg, which was causing a rotation, or would cause a rotation in this clockwise direction. Okay, when we wrote the equation for torque, we already labeled it underneath the clockwise section, hopefully. Okay, and so your final answer here would be 1.5 radians per second squared clockwise. Yes?
Are we going to end up looking at like how long it takes for it to reach a certain point, like how long it might take to fall?
You could, yeah, you could ask something like that. I don't specifically have that in the notes today or anything.
No, I meant like in the future.
It is possible. I don't recall if there's one specifically like that or not in the problem set, but it's possible. You have the information to do it. All right, guys, for the rest of the class period today, you can work on playlist 2 if you haven't yet finished it, because that is due by 11:59 p.m. tonight. Your torque lab, though, is due sooner than that. It is due before you leave today, because I need it on paper. So if you don't have that torque lab turned in, please go ahead and take it out. You can bring it up to my desk. There's already a stack of them. You can also start working on playlist 3. Real quick, I mentioned this before. If you have not already done so, please sign up for the District Practice AP test on April 13th at the Mark Henry Administration Building. I did get confirmation they are serving pizza, so you can go, you can take a test for free, get pizza for free, okay, get feedback from other physics teachers in the district. I may or may not go that day, I have to look if I can, but you'll be going through the test. They'll score it. You'll be able to ask questions. You'll score your own FRQs. There's QR codes on the flyers in the room. Please sign up. If you have questions as you're working today, please let me know.